Hello, my name is Alexandru, and today I will be presenting the paper Modern Consolidation Methods for Catholic Church Baroque Style from Arad Fortress, Romania. The presentation will be following this outline. This article highlights the results of a modern study conducted in the field of determining the load-bearing capacity of historic church-type buildings restored with reversible materials, technologies, and consolidation methods. The study was carried out on the Franciscan monastery in Arad Fortress, which was abandoned and no longer maintained. As a result, the bearing structure has deteriorated significantly over time. The construction of the fortress of Arad was ordered in 1762. The Franciscan church was already existent when the construction began. To determine the most effective structural analysis and structural intervention on the Franciscan church, several studies were conducted to help choose a minimum reversible intervention on the bearing structure of the church. The Franciscan monastery consists of three bodies: the church and the two bodies of cells for the monks. The total area of the church is about 500 square meters. The maximum height of the church at the towers is 42 meters, and the height of the monks' cells is 13 meters. The bearing structure of the monastery is made out of burnt brick masonry with a mortar binder. The structural system consists of masonry walls, pillars, arches, and vaults. Over the vaults, there is a wooden bearing structure of the roof and the roof cover. At an on-site visit to the monastery, several structural degradations were observed. Vault failures due to water infiltration due to degraded roof cover, vertical and inclined cracks due to the settlement of the foundation, degraded masonry due to water infiltration from rainwater, anthropic intervention like door openings made in the bearing structure, and a masonry wall with reinforced concrete elements. Vegetation grown on the walls and vaults of the building due to the degradation of the roof cover and bearing structure, and corrosion of on a reinforced concrete arch due to water infiltration and the freeze-thaw phenomenon. A pushover analysis of the structure was realized using the Tremori program to determine the bearing capacity and rigidity of the church. A nonlinear analysis identified the maximum efforts and displacements of the structure until the moment of failure before and after consolidation. The dynamic spatial analysis was created for a peak ground acceleration of 0-20 g. Following the spatial dynamic analysis, the vibration modes of the structure resulted, and also the results on the transversal axis X, the longitudinal axis Y of the structure. The vibration modes of the structure indicate a predominant solicitation of general torsion. On the transversal OX axis of the structure, the maximum horizontal displacement of the tower is 2 centimeters, and the maximum shear force is 6,200 kilonewtons. On the longitudinal OY axis of the structure, the maximum horizontal displacement of the tower is 5.7 centimeters, and the maximum shear force is 4,800 kilonewtons. A second pushover analysis was made which contains the church in aggregate with the two side buildings that contain the cells of the monks. The analysis was made with the same parameters as the analysis where only the church was modeled. On the transversal OX axis of the structure, the maximum horizontal displacement of the tower is 1.3 centimeters, and the maximum shear force is 15,000 kilonewtons. On the longitudinal or y-axis of the structure, the maximum horizontal displacement of the tower is 5.9 centimeters, and the maximum shear force is 18,000 kilonewtons. In order to maintain the rigidity of the structure and to increase the bearing capacity, minimal interventions were proposed with the composite materials which were produced by the Caracol company. The consolidation of the arches was done with galvanized steel fibers, lime mortars, and connectors, which can be seen in the image. The loads from the transversal walls of the church will be transferred through vertical steel bars to a proposed network of steel beams which lean on the perimeter of the structural walls. A consolidation of the walls will be done punctually with galvanized steel fibers, hydraulic lime mortar, and connectors. The consolidation of the towers will be done with the galvanized steel fibers, hydraulic lime mortar, and connectors as well on all four sides of the tower. The foundation, the consolidation of the foundations was done with an underpinning of the foundation that would stop the subsidence of the foundation and the cracking of the structure. The consolidation of the reinforced concrete arch and pillars will be done also with galvanized steel fibers, hydraulic lime mortar, and connectors. As for the unauthorized interventions, the door holes in the lateral walls will be rebuilt to recreate the structural integrity and the authenticity of the church, and the wall with the reinforced concrete frame will be demolished. The wood framing and covering of the roof will be remade in its entirety, if possible, using wood elements from what is left of the existing roof. To determine the efficiency of the consolidation methods, a third nonlinear analysis was made with the Tremori program that contained the sum of the consolidation methods described above. The analysis was made on the simple model with the church as an independent building. The analysis indicates that on the OX axis, the shear-based force grew to 10,800 kilonewtons, and the horizontal displacement at the top of the tower went down to 1.6 centimeters. On the y-axis, the force displacement diagram indicates an increase of the base shear force to 15,000 kilonewton and the reduction of the horizontal displacement of the tower to 4.9 centimeters. A comparative study was made for the results of the non-consolidating structure and the results of the consolidating structure. The comparative growth between the base shear forces on the transversal axis X grew by 74%, and on the longitudinal axis Y by 213%. The comparative reduction between the maximum displacements on the transversal axis X went down by 20%, and the longitudinal axis Y went down by 40%. There also was a comparative study for the vibration modes of the structure. In conclusion, this paper represents the first time in Romania that a study of the bearing capacity of a historic Baroque style church was done. The studies will continue with on-site testing to figure out the exact properties of the materials used in the construction of the church. The dynamic analysis utilized to diagnose the Franciscan church permitted the identification of the structural strength before and after the consolidation and the identification of the proposed consolidation solutions used to restore the historic architectural surfaces. The first nonlinear analysis in the Tremori program indicated that the structure may suffer significant structural damage after an earthquake with the ground acceleration of 0.20 g and requires structural consolidation. The second nonlinear analysis indicated that the building would have a higher structural resistance if the two adjacent bodies would be taken into consideration in the model. The structural consolidation was made with modern reversible technologies that do not affect the historical value of the building. The unauthorized interventions made to the structure were eliminated to re-establish the structural resistance and the authenticity of the building. The third nonlinear analysis indicates that the structural resistance of the consolidated building significantly increased compared to the unconsolidated structure. Also, this analysis shows us that the number of structural elements in the consolidated area of the towers that suffered failure modes were reduced. Thank you for your attention.